Good morning. I'm going to go just a little bit, a quick overview of what we're doing. Exascale block by block is a title I use. It's a bit of a teaser actually because, well, we don't already, well, it's not easy to make an exascale machine at this moment. So I'll go through the agenda a little bit. Some marketing slides will be passing by, so all obligatory. And some things about building blocks and challenges at scale. So Dell in News, that's one of my marketing slides I need to show. So we've been heavily involved in lots of HPC projects. These were a few in the news recently. You've heard Carl Schulze from TAC about the Dell system, Stampede. So one of the things that we have lots of strange experiences with the very large installations, which are not really HPC systems, but use the same type of ideas and technologies in HPC. So building blocks is just use off-the-shelf things. Standard switches, standard InfiniBand switches, coprocessors, storage devices, and some interesting modular systems. So building blocks is defining a simple building block is like using something that computes, something that has storage, something that has network, and connect these up in some way. Most of these, well, FAT3 designs mostly don't fit in this kind of modular thinking, so we need some other types of topologies in these kind of solutions. And if you scale out, well, you run into troubles because cost becomes prohibitive, cabling becomes a nightmare. Well, and managing it, and as you said, seen in the previous presentation, that actually managing these kind of networks on a software layer is also not just trivial. And practically, what can be a typical building block? So the C8000 is a kind of a modular chassis we use at TAC, which we can fill with single width sleds. We can fill with double width sleds, which can take more disks or Xeon Phi or other accelerator type cards. Or we can go through our standard enterprise level systems, but they offer kind of a very interesting density. So this is a 10U blade chassis, but it offers you 32 nodes of dual processor systems, giving you unaccelerated 36 teraflops in a rack. This is already not that bad. The only problem is this consumes 40 kilowatts. Looking at the accelerated, we're looking at 60 teraflops a rack. This is good for petaflop scale, but exaflop, it'll need something more. Building blocks in practice, actually TAC uses this kind of theoretical design of building blocks. Actually, you see modules of 5 units together with a switch, and another block of 5 units together with the switch, and just build this out in the direction you want. At this moment, there's only 1 Phi per node. We can have 2 Phis per node. So TAC is, let's say, at half maximum performance at the moment. One of these compute sleds that can accept accelerator cards looks like this. It's very simple design. Pull it open, put cards in, make it run. In this typical example, up to 2 Phi cards in 600 watts of power, 240 cores available. Well, it's talking to the machine and getting data in and out of the machine that will become an interesting challenge. This is not a recent slide. It's actually a rather old slide. And my previous company I worked for, we already did similar type of calculations, and we predicted 2018 would be around the time frame we would be needing or arriving at exascale. Well, we'll need a lot of interesting technology to make this actually happen. Because you see, well, each typical work group, 20 kilowatt rack, well, we're not thinking about 20 kilowatts a rack, we're thinking about more than just 20 kilowatts. It's more like 40 kilowatts a rack. So we're getting into problems with actually the power and cooling. Building block for compute, production storage, actually So the storage, using the same modular chassis, using a compute component and an array of storage components. Can use 12, 24 hard drives in one of those sleds. You can put up to 4 in a complete chassis, and this can give you a very interesting balance and, let's say, a simple and manageable design. At TAC, we actually use only 1 compute and 3 of those storage sleds, and we pair them up, so we have 2 servers connected to 6 storage sleds. As for Lustre, similar design. This is the standard server, typical server design. Then storage array connected to servers, redundant connections. Similar, but in a modular design. So the Ethernet building blocks, well, we're looking at, Dell has acquired not so long ago Force 10. Has some interesting technologies which are going forward, which is using ideas from Infiniment with the spine core and spine and leaf switch, so the distributed core switches. And actually, there's no single big switch anymore. It's all small switches working together as one big. Gives you very interesting patterns for easy scaling. Well, we know that easy scaling in these kind of spine leaf does impose some limitations when you go beyond a certain number of switches. So you will have to introduce new spines to into the layer to get scale. We know our Infiniment friends, Dell doesn't make this, so we have to work together with our friends from Mellanox or from Intel. But there's a new development focus on the bandwidth, well, actually using double rail or bonding type of channels, going to QDR80, FDR112, EDR. EDR is going to be very interesting because, well, we're pushing the limits of PCI Express speeds. So it will be interesting how to implement this. New topologies, we'll need to have new topology because the FAT3 of a huge scale, well, is almost impossible to pay for. If we're looking at a design like the Stampede at this time frame, it's a very interesting big machine. It's one of the biggest I've been working with. And there, you've heard Carl talk about the cabling problems they had. And if you have to make an exascale out of, at this moment, with the same technology we used at TAC for Stampede, we would have to multiply the system by 1,000. So this would be an interesting challenge. But you won't be able to cable this thing because, well, there's no room enough. There's no cable enough. One of the ideas would be using 3D torus with kind of, let's say, FAT3 zones. So each switch connects in non-blocking locally to the nodes and each switch is connected in a 3D torus to each other. This needs some extra interesting challenges for the software layer and the data movement and also the application awareness. Your application needs to be fully aware of where it's running, in which direction it's running, and how it's communicating. Because some applications, massive parallel applications, it won't matter too much. But if you have applications which really communicate within the application, well, you get into very hairy situations where the deadlocks, the performance, latency issues, and the contention of the network. So I'll go over a few of the challenges that we're looking at. So power is one of the problems. At this moment, Xeon Phi delivers us about 4 to 5 gigaflops a watt. Some calculations from the guys from DARPA, actually, they calculate that we need between 40 and 50 gigaflops per watt to reach exascale. So at this moment, there's no technology that allows us to do this. So 10 times the amount of cores in the same footprint and power, it's a challenge. Not only for an integrator like Dell, but also for our chip makers, Intel. Complexity of the network, new paradigms, 3D torus, FAT zones. Well, do we need a full non-blocking system? does it make sense to have a full non-blocking system? Well, let's say intuition says we'll have run into more problems building a fat-free topology than using more awareness in the application and in the scheduling system to make sure that the application is well balanced all over the cluster and uses as much as possible the local communication and only goes out to all the application sites or all the instances when it's really need to. Can we do this with traditional CPUs? Well, unlikely. Intel tries to make this happen, but well, we'll need something more than just Moore's law to make this happen in the next few years. So we will need accelerator or other concepts like we've seen this few days. Exascale design, well, failure resistance should be built in. So DK has talked a lot about resilience built into the MPI, but it's not only the MPI layer, it's also the application layer, checkpointing. So we need to be very conscious about it, because the bigger the system, the more components you have, the more chance you have statistically that there's something going to be failing. Looking at petaflop systems, we're looking at mean time to fail for about a few days. If we're looking at exaflop systems, we're looking at minutes, mean time to failure. Is always something going to fail. That's a given. Scheduling software needs to become more intelligent. Topology awareness, aware of where the data is, aware of where everything resides, and technology to keep up with the data needs. So data injection of the system, data absorption of the system, it needs to pick up speed, because at this moment we're not able to push data in and out fast enough of the system. Some new technologies we're looking at, DARPA study, well, there was a very interesting article they said, well, we can do it at this point in time. The problem is it'll take so much power, we'll need a huge power plant next to it, and it'll be dynamically using a delta of 50 megawatts. Nobody can deliver this delta of power in a short time frame. So this will be a very interesting challenge. Well, looking at low power CPUs, this is something Intel is working at. A CPU at 10 milliwatts, self-contained unit. Have many of these, make them solar powered. Would be interesting. Using new technology of the near threshold voltage. So making the efficiency of the transistors so high and using such a low voltage that you actually don't need any cooling anymore. And putting more cores in the same package. Something other, having a Xeon Phi with 2,400 cores instead of 240 cores. Having Y number of cards connected to X number of nodes, or have, for instance, 16. This is a special box that we have, which takes 16 accelerator cards, 16 PCI Express cards, and full 300 watts per card. And we can connect these up to 8 nodes to it. And this can be dynamically assigned to software layer. So we can just switch it in a software way, so we can dynamically change the amount of cards connected to one node. Or leveraging something different, like our friends from ARM. Well, ARM doesn't deliver the performance we are let's say, used to have in HPC, but there might be some interesting developments that make the throughput, because, well, if you look at this, this is the same double width sled that we put in the CA1000. So we can put up to 5 of these in one chassis. And this is 6 times 4 quad cores with storage or something else. You can put multiple ARM boards in it. ARM-based FPGA, new structures. And I'm very quick because I'm at my end of my presentation. And if there's questions, please ask. I have a very interesting video from TAC, which might be interesting to see.
I am Dan Stanzione. I'm the Deputy Director here at the Texas Advanced Computing Center at the University of Texas at Austin. We strive to be a leader in what we call advanced computing or research computing. So we build among the largest computer systems, storage systems, visualization systems, all in support of primarily scientific discovery, and in particular scientific discovery as it impacts society. So in this particular project, we're advancing our supercomputing capability to build bigger and faster systems that people use to simulate all sorts of phenomena, from the very smallest scale things around nanoscale materials to the very largest phenomena like colliding black holes and the formation of the universe. And also to do the sort of new large-scale data analysis that you need to do in genomics or in environmental observations or satellite data or anything else. You know, we're building a system with a 4-year lifespan. We're building it with a plan that starts 2 years before it's deployed, and you know, IT life cycles are pretty short, so you always want to reach and get the most aggressive set of technologies that you can. So we have the challenge of scale and a new data rate and very large switches going in there. Even the chassis that we put them in, all of our Dell products are also very new designs, and so the Dell Zeus chassis that we're using for the compute blades, we selected because it gives us a very dense package that can hold these Xeon Phi coprocessors, or big PCI cards, and you can't put them in a traditional blade. So we needed something we could put a big card into, but still give us a dense rack of systems. And so we were pleased to work with DCS on refining the design for that, so we could really pack those into the rack as densely as we like to. And then we're also using the Dell Scorpion chassis as the latest way to pack a whole lot of commodity disk power into a fairly small shelf. And you can go pop the disks out and replace them while the whole cabinet's running, and have a really easy way to do that without having to take cables apart. Physically, the system is of enormous scale. It's nearly 200 compute racks. It's nearly 500,000 pounds of computer. It's nearly 75 miles of cable. It takes over 5 megawatts. It has more than 100,000 processor cores of Intel Xeon processors. It has an additional several 100,000 cores of the Xeon Phi mini-integrated core processors, almost 500,000 threads of concurrency. It'll process close to 10 petaflops of overall performance, so that's about 10 quadrillion mathematical operations per second. It has more than 250 terabytes of RAM. It has about 14 petabytes of disk storage. So from just a physical and computational perspective, it's huge, and we expect it to do science, you know, of that scale. And once we get things tuned up, we'll start running the early science runs, where we'll put some users on and begin tuning the system to run hopefully some of the biggest simulations the world's ever seen.